All right, ladies and gentlemen, welcome back to another video with Mr. Kenton. This is AP Chemistry. We're working through Unit 3, and I have some good news. This is going to be the last video as it pertains to Unit 3. So that's exciting. You know what that means. Coming up on test time. I know you guys are going to be excited about that. All right, and so we're going to end Unit 3 by looking at, again, a couple of other techniques that we need to be familiar with as it pertains to solutions and how we can use those techniques to help us identify different properties of solutions, as well as some other energy components that we're going to be tying into this as well. And so in topic 3.11, there's a focus on spectroscopy in the electromagnetic spectrum. And you might remember the electromagnetic spectrum came into play when we were looking at Unit 1, when we were talking about different forms of light. Right? And unfortunately, this particular topic is not covered in depth in the textbook, but it's really simple. And it's really just, like 3 statements that you need to be familiar with as it pertains to spectroscopy and how it's used to determine things about atoms. Okay? So let's dive right into it. And again, when we think about spectroscopy, we've looked at photoelectron spectroscopy, we've looked at mass spectroscopy. There are other forms of spectroscopy that exist as well. And ultimately, spectroscopy works by shining different wavelengths and different energy light on a substance. And in doing so, it's going to elicit different responses from molecules that are interacting with those forms of light. And so what I want you guys to know is that when you're dealing with spectroscopy, if spectroscopy is using microwave radiation, then what that's going to do is it's going to cause transitions in your molecule in terms of rotations. So in terms of molecular rotational levels, that's what's going to be impacted by microwave radiation, right? Molecules will be rotating, and as a result, you're going to be able to pick up energy changes from that, right? When you're dealing with infrared radiation, if infrared radiation is being used within spectroscopy, then what it's going to do is it's going to be able to determine transitions that are taking place within your molecule in terms of vibrations, all right, looking at molecular vibration levels within that particular substance, right? And then ultraviolet and visible light is going to be radiation that's associated with transitions in electronic energy levels, right? So you expose a metal, for example, to UV or visible light, it's going to cause electrons to move between different energy levels, right? And so, again, our purpose in sharing this with you is so that you can understand what types of changes different forms of light can cause at the molecular level. So to kind of summarize here, microwaves cause changes in molecular rotation. Infrared light is going to cause changes in vibrations within the molecule. And then UV and visible light is going to cause electrons to move between different energy levels within the atom. And this is going to move very nicely into the photoelectric effect. And if you recall, we examined this in Chapter 6, Section 2, when we were talking about the energy required to cause an electron to be ejected off the surface of a metal, right? Remember, nature of energy, this is Einstein came up with this idea, and he used the assumption that light was given off in specific chunks, just like Max Planck had communicated, to help explain the photoelectric effect, right? And remember, the photoelectric effect is simply this idea that if you shine light on the surface of a metal, it will cause, if it has enough energy, for electrons to be emitted off of the surface. And so Einstein concluded that energy is proportional to frequency. And again, we saw this equation in Unit 1, E equals h times nu, where h is Planck's constant, 6.626 times 10 to the negative 34th joule seconds, and nu would be the frequency of the light that you're dealing with. Okay, and so if we know the wavelength of light, we can calculate the energy in one photon or packet of that light. So remember, we can use the relationship of speed of light equals lambda times nu, wavelength times frequency, and the relationship of energy equals h times nu, or the frequency, to figure out that particular energy for that particular substance. Okay, so I imagine that the photoelectric effect stuff that we're looking at, that should be a review to us. That shouldn't come as a shock or anything new to us. All right. And so the last technique that we need to look at is called the Beer-Lambert law. And that should say Lambert, L-A-M-B-E-R-T. And this is going to be found on page 532 in the text, looking at the closer look section. And this is going to have direct correlation in our understanding of solutions specifically. Because the way that the Beer-Lambert law works is that you take a concentration of a solution, and what you should be able to determine is that the higher the concentration of the solution, the greater the amount of light that it'll be able to absorb, right? And so if you look at this particular graph in the upper left-hand corner, that's exactly what it's showing. When the concentration is really low, the solution doesn't absorb anything. But as the concentration increases, we see that the absorbance values of this particular solution is going up. And that's a trend that we should see as a solution becomes more and more concentrated. It's able to absorb more and more light because you have more and more of those particles that are present. And so the Beer-Lambert law is expressed with the following equation. A equals epsilon times C times L. Now this is an equation that is on your reference sheet. And A is a measure of the absorbance. It's looking at the light that's being absorbed by the solution. The epsilon is the molar extension coefficient, has those particular units, inverse molarity, inverse centimeters. C is going to be concentration, so the concentration of your solution, and L is going to be the path length, right? That's going to be the distance that the light has to travel within the solution that we're dealing with, right? And in terms of Beer-Lambert law calculations, the path length is also a factor, but it is often held constant for applications of the law to determine concentration. So typically, you might be given absorbance values, epsilon values, and L would be held constant. You could use that information to calculate C, right? And we'll even see how you can use the Beer-Lambert law later to determine kinetic information, so the rates of reactions. And so I just wanted to show this to you guys so that you can see that for our solutions, that there are some things that we can quantitatively measure just outside of concentration and how that's helpful in us understanding how a solution functions. All right. Again, the Beer-Lambert law, that equation is on your reference sheet. And ladies and gentlemen, that's all I've got for you guys. So if you have any questions, make sure you fill out the Google form, get that to us, or ask questions in class, and we'll be happy to address those. That's the end of this particular unit, which means we're coming up on a test pretty soon. So thank you guys for joining me, and I look forward to seeing you guys again soon. Take care.